Hello, YouTube. Hello, Ryan. Hello, Joe.
Hey, Mike.
Hey, Michael.
Hey, all. If you're out there watching the live stream, please feel free to throw some comments in, or I guess if you're watching later in the comment section below. But live comments, we'll try to make them part of the show. And with that, let's kick off the podcast. Joe, Ryan, welcome to Talk Python to me.
Hey, it's great to be
here.
here.
Thanks so much for having us.
It's fantastic to have you here. I'm really excited to talk about earth science and all the cool large-scale computing stuff and cloud computing and things like that with you. It'll be a lot of fun. So really looking forward to getting into that. Now, before we dive into the topics, let's just start with your story. Joe, I guess you go first. How'd you get into programming in Python?
Yeah, so my path came through grad school. I was studying civil engineering and climate modeling as a graduate student at the University of Washington. And I was in a computational hydrology group, so we were doing lots of computer things. And my PhD advisor at the time was like, "We want to do Python stuff. I don't know anything about it, or I don't know much about it. You should be the kind of the guinea pig student to like bring our group into the modern era." So kind of threw me to the wolves, and I ended up really kind of taking on a role that like not just learned it, but then started teaching other people, and I ended up contributing to open source packages, and kind of the rest is history.
Oh, that's fantastic. What were you using before? You said you brought them into the modern era. Where were you coming from? What was the dark ages?
Some terrible mix of like Perl and C Shell and C and Fortran and a bunch of other shell scripting languages. So it's a total spaghetti land.
Wow, that is a spaghetti land. I would say Python and Jupyter in the SciPy stack probably sounds a little simpler.
Yeah, the connections are a little more natural for sure.
Indeed. How did people receive it?
It's been great. I think for me personally, it was like quite the revolution in what was possible. But then passing it around the lab and then around kind of the research community since then, I think it's been overwhelmingly positively received, and we're doing totally different things than we could have done without it. And I think that's the big change.
Yeah,
it's not just that it's like a little easier to program, but that you can do things that you couldn't have done before.
Interesting. Yeah, were people worried that, coming from C and Fortran that Python wasn't fast enough? They're like, we can't use this. This is one of these slow scripting languages. Or what was it? You had already proven it was fine.
No, you hear that on occasion, but I think the developer velocity like outweighs that in 99% of the cases.
Yeah, I agree.
You can always optimize the 1% case further.
For sure. Ryan, how about you? How'd you get into programming in Python?
Kind of been a lifelong programmer. So I was actually just thinking back when you asked that, I think I wrote my first basic code at age 7. My dad worked for IBM, and so I'm like really been like a kind of lifelong computer nerd. Drifted away from that a little bit in college, where I majored in physics. But then, in graduate school, I did a PhD in climate physics and chemistry at MIT, and I had a huge need for scientific computing in that. So all of a sudden, sort of my computer, stuff started really coming back full in the center of my world. And it was a MATLAB shop, MATLAB Fortran was the stack, there. And after I sort of did my first project around 2006, 2007 in MATLAB, I decided, I'd been doing open source, hackery in other languages for many years. And I was like, I need an open source scientific computing solution. So I tried Python, got into Python around 2008. So that was when I've been at it long enough to have like compiled NumPy and
that's like really when NumPy was basically coming out, is right around that time.
Before Anaconda and the other one. Then just rolled with it ever since. And I was like the early adopter Python guy around there. I helped get a lot of other people into it. But it was still always just in my own, projects, right? Like there was no community. I really got into open source community development probably around 2014, 2015, when I discovered Xarray. And that is like the project that really like turn me from just a user to a contributor.
Fantastic. Yeah, that's like multi-dimensional NumPy goodness, right? Yeah, we'll dig into it. Yeah. Was that other distribution to Anaconda? Was that Canopy?
Yes, Canopy.
I see out in the audience. Thank you, Erie. Cool. The other one I was thinking of was Active State. So yeah, there's these different distributions people can get for optimizing for different stuff. It's great. All right, how about now, Ryan? What are you doing day to day? It sounds like you both are still doing research, university-like things.
Absolutely. So I'm a professor here at Columbia University in Lamont Doherty Earth Observatory, and I sort of manage a medium-sized scientific research lab and teach at the university. But then I wear this total other hat as an open source developer and contributor. And so that can be sometimes a little exhausting to try and wear both those hats at the same time. But I really enjoy it. Our work in our lab is focused on computational oceanography, trying to understand the role the ocean plays in the climate system, particularly the role that small scale ocean processes, eddies, fronts, instabilities that are occurring at the, say, 10 to 100 kilometer scale, how that sort of turbulence and variability influences a large scale ocean and the role it plays in our changing climate.
Right.
The way we do that research is by working with large scale satellite data from NASA. So I'm involved in the NASA Surface Water and Ocean Topography Science Team, a new satellite mission that's launching this year. And we do a ton of numerical modeling, simulating the ocean with computers. And so, at the end of the day, we're doing data analysis, some of which is sort of traditional statistics and visualization. Increasingly, machine learning, AI, ML are part of our toolkit that we use to try and understand the ocean. But the bottom line is, just working with a lot of data every day, diverse projects, and that has really forced me to center the rule of these tools in our work and recognize them as sort of, that is our, a lot of my colleagues, in other buildings at our lab, they'll have $1 million mass spectrometer. They have an instrument they use, they do science, and they
some crazy laser or something, right?
Yeah, and they turn the crank, and we're a data-driven lab, and so I think of Pangeo in a way as our instrument that we all contribute to and maintain, that then helps us to do all of the research projects that we want to pursue.
Yeah, how fascinating. I think you talked about running a research lab and then also doing this open source thing, this dual hat thing. I think the world may have changed, but when I took a couple computer science classes at university, when I was my undergraduate degree, I didn't feel like a lot of the instructors or professors there really had much real world experience in programming and stuff. And I think things like this, like contributing to Xarray, it must give you this really grounded sense of not only these are the tools that you can use, but here's how it works. These are the people doing. You're in the trenches. Do you think that makes a big difference?
I think we have a major education problem around computational science in that there's no, and I say this as someone a university professor, we have no curriculum to teach someone how to be an effective computational science, and particularly in the context of open source community driven software development. We have computer science classes that will teach you a lot of great things about algorithms and data structures and even machine learning, but they won't teach you how to write effective software. And as you said, currently we assume you have to learn that in the trenches, just getting into a project. Maybe you work at a company. For me, definitely, I upped my software engineering game so much after I got involved in community open source, because there were people like Stefan Hoyer, Google staff engineer, who were reviewing my PRs, right? And so that was huge. But I wish actually the university could teach this skill set, because I think it would help the world a lot.
Yeah, I think it would as well. I think we can absolutely find space in the curriculum for it. I think math might need to give up a little bit to allow for computational math rather than symbolic math. If I could pick, I don't want to do realist too much, and I do want to let Joe get a chance to talk as well. But I think geometry and the going through proofs and the thinking about how do I take axioms and using proofs to solve problems is exactly the same mindset in the way of thinking as solving a computer program or solving a problem with a program. And I haven't applied geometry that much, but I sure applied a lot of computers. So anyway, I just put that out there for people.
You might be a little biased.
I may be a little biased, although I do have 2 math degrees for what it's worth.
Yeah, there you go.
But I'm still willing to put geometry out there. Anyway, Joe, how about you? What are you doing these days?
Yeah, so I wear a couple hats as well. My main hat is I'm the technology director at Carbon Plan, a nonprofit that's working on the climate problem. And there our focus is really on improving the transparency and the scientific integrity and quality of climate solutions. And we do that by building open source tools and open data and doing research into the various climate solutions that are out there. So we use a lot of open source software to do that, and we build a lot of open source tooling, including software, to help tell stories about different climate solutions. The other hat I wear, I'm a scientist at the National Center for Atmospheric Research, where that part of my role looks a lot like Ryan's day-to-day. We study different things, but I work with big climate model data and do data analysis and all of that.
Yeah, it sounds really fascinating. At Carbon Plan, what kind of data do you all use? Do you like hook into electric grids? Do you analyze like the mixture of electric grids or transportation, or what kind of problems and things are you solving there?
Yeah, so it's a bit of everything. We do big data, little data, and everything in between. But so like one of the areas we spend a lot of time working is in the area of forest offsets and trying to ask questions about the quality and the potential of using forests as a climate solution. And so there we're using everything from in situ observations, where people go out and measure trees with a tape measure, and they do that every 5 years. And that's like actually a fairly small data set, even though there's a lot of trees out there. There's only so many measurements you can make. And then we also work with climate model data. We study climate risk to forests. And so there we're building models of future forest fire risk and trying to understand how that's going to change in the future. So that's like big data stuff. We're doing lots and lots of model building and machine learning and that sort of thing on top of climate model data.
That sounds fascinating. You and I are both in the Pacific Northwest, and last year was not too terrible for fire season, but recently we've had some pretty bad forest fires up here, and it's definitely concerning. So
yeah, it definitely feels like I'm studying the world around me more than ever when we're working on these fire problems, and then also experiencing the smoky weather that we've been having in the summers in the West Coast the last few years.
Yeah, it's been pretty crazy.
And I mean, I think that's a theme in climate science right now. It's gone very quickly from this academic problem to something that so much of society and our economy is engaging with. Companies, are just getting to work on adapting to climate change because they're feeling it in their bottom line. And it's different than things were 10 years ago.
Well, that's good to hear. I'm both pessimistic and optimistic about how things could go. There's so many cool discoveries. Folks like you are using, Python and computation to really understand exactly what's happening and keep your finger on the pulse of where they're going. And then also I see, a mom and her one small kid in a Chevy Suburban next to me, idling in traffic. And it's like, I don't know. People do have to internalize it, I think, a little bit more, but I wonder if it is maybe in business, they're starting to react a little bit sooner, right? I think companies feel pressure of economics sooner than people do a lot of the times.
Yeah.
I don't know. Where do you guys stand?
I know. I think that's true. I think there's also social pressures that are pushing companies to act soon, and so it's not just sometimes it's altruistic, but also I think there's marketing involved and
right. You just don't want to look like the bad company if they can put on a good image and it's worth it. But whatever gets them to do it, I don't care if it's.
Yeah, that's what I was just gonna say. I think we don't have to shame that. I think that there's a lot of action that needs to happen in a lot of sectors right now. And so to the extent we can motivate that through one mechanism or another, that sounds like a good idea.
Yeah.
We're getting like maybe down this climate rabbit hole, but this is probably the most important issue of our time. So let's go down it. I mean, you got to distinguish between the terms we use are mitigation versus adaptation, right? So mitigating climate is doing things like burning less fossil fuels that are going to reduce the potential impacts of climate change. Adaptation is just accepting that climate change is happening, it's going to happen, and changing our behavior, like infrastructure, planning. And so when I say I see a lot of companies taking action, I see especially a lot of companies taking action from where I sit on adaptation, using Earth system data, using our projections from our climate models to make business decisions under this changing climate. Mitigation is what we've been calling for decades. And that's where like the Chevy Suburban comes in. And, you know, I guess I really push back against the idea that like personal choices are like an important part of mitigation. I think this narrative that's actually been counterproductive. Like, I don't think we need to rely on personal, like ethical choices about like which type of like, you know, bags to bring to the grocery store. I mean, like it's important, but like this is a very, very large scale.
It's solving the problem, like very, very much on the edges when you're just going like, but there's this huge middle part. What are we doing
We
here?
need global scale regulation around carbon emissions in order to mitigate climate. And that's a political problem.
It is. It is.
Yeah.
Well, the renewable energy story seems to be coming on faster than people thought recently. So there is a lot of hope in that space. Now let's talk. You both mentioned a little bit of this sort of blend of like open source side of things and then the science side of things. Let's just talk for a moment about just some general best practices with open source and science and stuff like that. So yeah, it's one of the things I guess is Ryan, you talked about having people like these high-end software engineers reviewing your code and stuff. And I suspect there's a lot of lessons you've learned that you can kind of bring back to the science world from that open source experience.
I think there's this whole spectrum of open science, right? And open source activities, right? So right now it's pretty common in scientific fields to encourage research projects to publish their research code under an open license or put it on GitHub or something like that. And there's, I see that as just like a very, very first step towards a much more transformative way we do science as a community, right? Like, as you well know, like just putting a repo up on GitHub has essentially no impact, right? Like, yeah. If no one uses it, like if someone pushes a commit and in a forest and no one hears it land, like, okay, great, like you checked a box. The real goal of open science is to encourage more reuse, more collaboration, and accelerate the velocity of scientific discovery. And that takes more than just putting your code out there. It takes, and of course, putting your code out there is the first step, but it actually takes making sure people can run it. Like they have the environment for it. Like it can access the data that it needs to run, that they understand what it can do, that it's coded in a way that is extensible and modular, right? And all of those things are a lot more than a license. They're about essentially writing good scientific code. And so, I do think that just the process of getting involved in open source is a huge form of education for scientists about how collaboration can work, not just even in code, but in general. The way the collaboration process works in a well-functioning open source project is kind of miraculous.
Yeah, it absolutely is. And there's a lot of barometers people use when they go and look at an open source project to decide, can I trust this thing, right? The obvious ones are like, how many stars and forks? Like, is it a popular thing that people seem to care about? But others are, does it have tests? Or, does it seem to be operated in a way that is going to lead to contributors being able to contribute? And, the software evolving over time in a way that they could depend upon, right?
Yeah, I think another thing here that's really important to think about is what the incentive structures are for a researcher working on a scientific programming problem.
Absolutely.
And for most graduate students or researchers at institutions that Ryan and I work at, the goal is to write a paper or to produce a data set. And the software has been kind of thought of as like a tool you use to get there, but it's not necessarily a tool that you fix up or improve along the way. And I think one of the things that we've been trying to do is kind of break that pattern a little bit and think of that, like the whole ecosystem of tools that we're working with is improvable, so that we don't have to reinvent the wheel. And, individual researchers have, maybe just speaking for myself, being able to say, okay, I'm going to rather than take the like shortcut path to get to the end of the paper, I'm going to like improve the ecosystem so that later on I can reuse this improvement, but also Ryan and others in the community can reuse it. And that's like a fundamentally different way of thinking about the tools you're using.
That's interesting. It sure is. I've only spent a couple of years in that space, but my experience was so much of the code, at least traditionally, had been written just to solve a very focused problem and not in a way that could be adapted to future problems, right? It'd be like, well, we're changing the algorithm or it's slightly different data. So we'll make a copy of this script and we'll copy it over there. And we'll just like, maybe there's not a single function in the whole thing. It's just top to bottom. And I suspect adopting some of these techniques to sort of produce more of a library out of it, even if you put it on GitHub and nobody comes, it still would benefit you in your research over time, I would imagine.
And I would say that is a big part of Python and why Python is a good tool for science, because it is easy to build higher level abstractions. Like coming from the MATLAB world, you basically got MATLAB and its toolboxes, and then you got like your scripts. Yeah. And like there's like this hard divide between like the platform and the tool and like your own work. And so like you're used to thinking, well, these are like the primitives provided by like the tool, and like here's what I have to do. But Python allows you to build very flexibly and has this great ecosystem, right? And so, I mean, I think this segues naturally into Xarray. Like, many of us in 2014 had our own sort of private version of a code that did what Xarray did, thinking like that's code that needs to live in in user space. That's not a package provided by the ecosystem. But then once sort of Xarray started to catch on and we realized how powerful and how cool it was and how well it would, like what a solid foundation it had, many of us immediately stopped working on our own sort of private Xarray like thing and started contributing to Xarray. And we've seen over, say, the past 5 or 6 years, this really steady growth in like the capabilities, both in terms of features and robustness, like of Xarray, that we never would have done if there hadn't been that coalescence around like, okay, we're all going to work together on this. Yeah.
And then you have these knock-on effects, right? There's now other libraries and other systems that use Xarray. And so if you're programming against it, it's super easy to plug into it, kind of like what Pandas and Dask are doing. Like if you program against Pandas, you kind of automatically get like this scale up version because Dask is just Pandas, but more, right?
And you don't have to write code to like read CSVs.
Yes, exactly. So I gave the elevator pitch for Xarray, but let's go ahead and dive into that and some of maybe give us the story for Pangeo, where Xarray is one of the sort of umbrella. It's covered under that umbrella.
Yeah. So I'll start, but I think just to take maybe a slight step back and say what Xarray is one more time. I think so. Xarray is a Python package for working with multidimensional labeled arrays and data sets, and it integrates with NumPy and Pandas. And in many ways, you can think of it as a multidimensional Pandas. And so it's used really widely in the climate science community and the geosciences, but it's also used in fields outside of the geosciences, like
could be finance or all sorts of things, right?
Yeah, so finance and biomedical and bioimaging, et cetera. So
give us a sense of like the data that you might load up off of some oceanography
Yeah,
oceanography studies.
Oh yeah, Ryan, go ahead and take the oceanography example.
Sure. Like something I think like our go-to data set for oceanography is like ocean sea surface temperatures. Satellites observe the ocean from space, infrared or microwave observations can tell how warm the water is. That gets processed by NASA. They distribute essentially a bunch of NetCDF files that are up on like basically an HTTP or FTP server, one file per day for the past 30 years. Quarter degree resolution. Each file is a couple, 10, 20 megabytes or something like that. And we want to do an analysis on that data, right? And so X-ray can open that individual file, but it can also open that collection of thousands of files as one coherent data set object.
Interesting. So do you give it something like a directory and a file pattern, and it somehow does a sort and then loads them up together?
Yep, it can do globbing. You can pass it a list. And actually, that is one of the killer features of X-ray that I think brought a lot of people into it, because we were all kind of used to like writing code around files. Like, okay, I've got to do this analysis. Here's like 100 files for like each file in my list of files. Do this, right? And instead, the workflow changes with X-ray. It's like, okay, open multi-file data set. Mean done, right? Like,
Right.
And so it's just like this cognitive load that's lifted.
That's cool. Yeah, especially in the data science space, I see a lot of these things, and it's almost about learning about the packages and the way that you can use them. Like an example that really quickly comes to mind for me is like, if I wanted to get a table out of an HTML page, out of a website, and then pull that in and like process it, I could go get the page with requests. I could do some beautiful soup thing to find the table, and then I could, I don't know, try to parse it or something, and then convert the elements. If they were really supposed to be numbers, you got to parse them as numbers, and then get that into some data structure. Or you go to pandas and you say read HTML tables bracket 2 or something like that. Like, those kind of things seem to appear so much in these data science libraries. Like, oh, you could do this big, long computer sciencey thing. You could call this function over here, and you got the same outcome. And it's really about knowing about that those exist, right?
Yeah, totally. Okay, to go back to your original question, I mean, we can come back to X. I think we spent a long time on X-ray, but I wanted to make the connection since you have the Pangeo website up on the screen.
Yeah.
After a couple of years of working on X-ray, a handful of us were starting to think, okay, we're onto something here. Mm-hmm. This is really the beginnings of, kind of a platform for doing research. So we all got together at Columbia University. Ryan hosted a workshop in late 2016. And I don't even remember what the name of the workshop was. PIAOS, Atmosphere Ocean Sciences, or something like that. It was a name that got dropped pretty quickly. But the idea was that we were like 20. It was probably 20 of us that worked on X-ray and Dask mostly, and it was kind of a mix of software developers and scientists. We got together and like just kind of shared out the use cases that we were wrestling with and the problems. And out of that grew the Pangeo project and a few ideas. So the mission that you read on the website today is like what we wrote that weekend, which is, to try to tackle a few key problems that we're facing our community, mostly big data, reproducibility, and really aiming at supporting a software ecosystem that connected all those dots. And since then, the Pangeo project has grown into a wider community project that has a lot of software packages involved, not just X-ray and Dask. Mm-hmm. So that's the origin story. It really started with X-ray as the beginnings, and
okay, interesting.
A bunch of other things.
Yeah, very cool. Maybe we could talk a little bit about the other packages. So we've got X-ray, and then there's a list of packages on the website. Iris, I know y'all don't do too much with Iris, but maybe just tell us really quick what that is.
Yeah, Iris is it sits at the same level of the stack as X-ray. So you're probably using either X-ray or Iris. Iris is, I would say, it's maybe a little bit more opinionated than X-ray in the sense that it's scoped to geo data or like data, or that has things built into it that are like more specific to that domain.
Like some of the specific file formats, which I'm not familiar with, but like GRIB and
No, actually, Xarray gets all of those file formats.
Okay.
It's more. I think it's more about the API, like an understanding that like what latitude and longitude actually mean, and like supporting things like regridding directly rather than say through third-party packages like we would use with Xarray. It's a great project. And it is in many ways very complementary to Xarray and highly interoperable as well. You can like Xarray to Iris dataset, Iris dataset to Xarray. You can think of them all as wrappers of higher level data structures around arrays, right?
Okay.
So like, many of us have probably written. If you work with NumPy at any level, you probably had a dictionary with NumPy arrays in it. Like multiple different arrays you want to keep together. And at that point, I would say like just use Xarray whenever you're starting to program in that pattern.
Yeah, because that's basically what Xarray is, right? As how do you label it? That's the keys, and then multidimensional is multiple arrays, right?
Yes, and then understanding relationships between these, and then metadata, a huge part of this, right? Like so Xarray, both Xarray and Iris and anything in this space is going to really understand metadata that comes with those things. So things like units or conventions that tell you how the variables are related to each other, and then it can do things with that metadata computationally, not just like drag it around for posterity, but actually leverage it to make certain syntax or certain computation.
You filter by all the ones that are tagged by state or whatever. Interesting.
Yep.
Okay. So then the next one in the overall banner of Pangeo is Dask. I've had Matthew Rocklin on the show before to talk about Dask, but it's been a while. So maybe tell folks about Dask.
Yeah. So Dask is it's a library for doing parallel computing in Python, and it has a bunch of different containers. And so there's Dask Array, which is what Xarray uses, but there's also a Dask data frame, which does kind of parallel chunked operations on Pandas data frames. And then there's the like catch-all, the Dask bag, which does graph style parallel computing. So where this comes in for Xarray is that, and actually for Iris as well, since we were just talking about Iris, but the arrays in an Xarray data set can be backed by a Dask array instead of a NumPy array. And by just kind of swapping that out, it's almost a behind the scenes swap out. You do a dot chunk on your Xarray data set, and then your operations are going to be handled by Dask, which means they're going to be streamed through the Dask scheduler. You'll be able to scale out to a cluster of workers and do, instead of, say gigabyte style operations, you can do terabyte scale or even petabyte scale someday. Data analysis. So Dask is the thing that gives Xarray its horizontal scalability.
Yeah, very cool. So scaling across machines. Now, when I learned about Dask, I saw it as it's like the local pandas or the other types of things that models, but you set up a cluster and it runs there. And then when I spoke to Matthew about it, I realized, he pointed out, that it's useful even on a single machine some of the times, right? If you've got a ton of data but not enough RAM to hold it, or you even have like my pretty simple computer here has 8 cores. If I run something on Pandas, I get 1 core worth of processing power, right? So maybe Joey, you're shaking your head, like tell people about like that use case.
Yeah, so Dask has a bunch of schedulers, and some of those are local schedulers that run on a single machine, and they can either use Python's multiprocessing module or threading, multiple threads, to do computation. It also has distributed schedulers that might live on Kubernetes or on an HPC machine. There's now companies like Matt Rocklin has gone on to start Coiled, which has managed Dask clusters for you. But the idea is that, like, at a small scale, when you're using the threaded scheduler, it's going to stream computation. So when you say taking the average of a terabyte size array, it's going to like use its chunks and process those chunks one at a time, and then aggregate those process chunks to the final result.
Yeah.
So,
a lot of times if
yeah,
it's the simple path of you go find some tutorial or example code or something on Stack Overflow, it's just like, well, first you just load this up, you just read the CSV or you load the JSON file, and then you go over it like this. And you're like, but I have a terabyte of data and, you know, 16 gigs of RAM. And so you need this sort of iterative streaming style to get there.
The brilliance of Dask, the game-changing flavor of Dask is that for many cases, the user doesn't really have to rewrite their code at all to scale out, right? So typically with Xray, like when we teach it and we really want to like get people the sense of the power, we like start by downloading like a 10 megabyte file and opening it with Xray and doing some analysis. And then they like learn the API and, you know, they use it, and then we point it. Then we sort of point people to like a massive, you know, 100 gigabyte data set in the cloud and a Dask cluster, and we say like write the same code, and it like just works and is pretty fast, and it is able to scale out without much really any expertise on the user's side about distributed computing. So I love that feature. On the other hand, I've also come around to the feeling that it can sometimes, you know, it's a double-edged sword, because some things actually just fail if you don't think hard about the parallelization strategy. It's not magic. It depends on the operation that you want to do. And so the flip side of that ease of parallelization is that sometimes users will think Dask is smarter or more capability than it really could ever be, and expect it to just automatically parallelize anything, even say just IO patterns that are just not parallelizable, not scalable, right? Or other operations that are just not can't be accelerated.
Yeah, it seems like it just automatically fixes the problem. It just makes it faster with magic programming dust, and then like obviously at some points that comes undone, right?
Totally.
You mentioned Coiled, Matthew Rockland's company that he started with some other folks, I believe. And this is a really interesting story. Like we talked about how you've got your Xarray light code, or you got your Pandas light code that you just wrote for yourself. And then by sort of adopting one of these libraries and maybe even contributing it and like building it up, you get these knock-on effects, right? And so I gave the Pandas to Dask example. And like, here's the next step in that chain, right? Like now you have, I can just spin up a cluster on the cloud automatically through Coiled with like 1 or 2 lines of code because I built on Dask, because I built on Pandas, you know, like that chain just keeps going of like how it all sort of this synergy between all of them.
Absolutely. And I mean, I would say like, it's not just like coincidental. Like Matt Rockland was at that Pangeo meeting at Columbia, like in 2016 or whatever. And actually we've watched this evolution. So a big part of what we have been doing in Pangeo is experimenting with cloud computing. I think a little bit earlier and more sort of in a different way than a lot of the other scientific community was. I think, and we can thank Matt for that to some degree, because we kind of, the story with Pangeo and cloud is that after that workshop, we wrote our first proposal to the NSF, and we got a grant to like develop some of these stuff and develop Pangeo and support scientific use cases. And what we had put into that original grant were like, we had a bunch of servers that we wanted to buy to like host data and run stuff, because that's what you do like when you write a scientific grant, right? And NSF asked us to trim our budget, and we decided, okay, we'll cut out these servers, but why don't you give us some credits on the cloud? Because at the time NSF was running this pilot program called Big Data, where they were granting, there was like a partnership with Google and Amazon and stuff. And so we got like $100,000 worth of Google Cloud credits. And we just started playing around to see how well we could make this stack work in the cloud. And Matt was instrumental actually at that time. He was really involved and was helping us figure out like how to deploy stuff in the cloud. And we learned all about Kubernetes and object storage and like all of this stuff. And it was incredibly fortunate for us to have that, because I think we really figured out a lot of stuff early on about how scientific research can interact with cloud computing. And that's where a lot of our focus and energy is today.
That's cool. Yeah, there's a lot of interesting things about large data sets, right? You can put them, as you said, in object storage, and then people can come into that cloud and like use the data without trying to download it or move it around. Or like some of these data sets are terabytes, right? And what are you going to do to get those shared, right?
Yeah, I know some of them are petabytes at this point, and
which that's terabytes you can do. Petabytes, that might be like a little bit beyond what your ISP is going to let you do to download.
That's right. Yeah,
or you can get a hard drive for it, right? Where are you going to put it?
Yeah, exactly. Yeah, I think that's the thing that our work on cloud computing really unlocked for us was this idea that we could federate access not only to compute, right? Like everyone kind of knew, yeah, you can spin up a VM, but federating access to the data in a way that was, infinitely scalable, both in terms of access, but also in storage, is a total game changer. And so, as we've gone down this rabbit hole, and we've gone fairly deep at this point, the idea of putting data in object store and letting anyone in the research community access that has kind of revolutionized the way we think about what scientific computing platforms should look like going forward.
Yeah, absolutely. It solves like half of the problem. One is the computational time and power, but the other is just the storage and the data and the memory and all those kinds of things, right?
Absolutely. And, I think data providers are really reckoning now with what the cloud means, right? Because, what we had seen in geosciences and climate sciences is, there were a lot of data portals out there. An agency or a group would decide, we have a data set we want to share. We have this data we want to share. Let's make a portal, which was almost always sort of a highly customized website with a browser. And maybe you had to click through to do some JavaScript and do it. Like you had to interact with the browser to get data files. And then you would get some data files. And, it's in maybe it seemed like a good idea. There was reasons why they wanted to have a portal, but from a user point of view, especially an expert user point of view, they're just incredibly frustrating to interact with data that way. And so with cloud object storage, I linked in the chat this blog post I wrote about this, my fantasy about it's this facetious post about how to create a big data portal. And you can see there's one step. It's upload your data to S3, right? And
exactly.
It's I think it's provocative, but I think the fact is there's a lot of vested energy, expertise within the scientific community about how to build and maintain these really bespoke data access solutions, when I think really we should be moving to we should just really be using object storage and the scalability of cloud style computing to distribute scientific data. That doesn't mean we need to just go all in on AWS, although actually that's exactly what NASA has done. But there's a lot of cloud storage things that provide a really scalable base layer of storage for internet enabled computing. There's Wasabi, alternative to Amazon. There's Cloudflare now is launching a data storage service, which I'm super excited about.
Yeah, put it on the edge. Interesting. Yeah, and you might end up with a copy of that data. Maybe you have a copy in AWS, a copy in Azure, maybe even Linode, DigitalOcean, places like that, right? But that's only 4 or 5 copies, not every researcher trying to figure out how they're going to deal with it, right?
Exactly. Yeah. Or you outsource that sort of mirroring to a service that knows how to scale that sort of thing. Another really interesting player in this space is IPFS and the distributed web. And where we're at now is people are very excited about in science are about S3 and cloud computing, but on the other hand, the scientific community is wary of being too dependent on the big tech giants, and it always has sort of a do-it-yourself sort of distributed approach to infrastructure. So I'm really excited about IPFS Interplanetary File System, which is a distributed yet highly performant way of sharing petabyte scale data on the internet.
Oh, that sounds really interesting. Let's see, really quick. James out in the audience is asking, are there any Pangeo specific resources to help with that transition, that jump from the workstation to cloud computing?
Yeah, I think this is a good opportunity to show off and talk about the list of tutorials and examples that we have. So I think Pangeo has a collection of Jupyter notebooks that show how to use. Yeah, so this is gallery.pangeo.io, and there's a list of Jupyter notebooks here that walk through kind of real world examples of working with large geoscientific data in the cloud. And so I'd encourage people that are listening to pull this site up and take a look. But
I'll put a link in the show notes so people can find it as
perfect.
well.
Yeah. So I think this is a good example of like one of the best resources we can point folks to.
Okay.
But I mean, to get a little bit more specific, the idea is that actually you don't have to change very much at all about your workflow when moving to the cloud, right? That's what we are aiming for with Pangeo. And a key part of this, and sort of that another pillar of Pangeo that we haven't discussed yet, is Jupyter, right? So Jupyter is a key part of our effort. We work very closely with the Jupyter, developers and also the team at 2i2c, who I know you've talked to recently, right? And the Jupyter has been, I think, an amazing sort of Trojan horse for like cloud computing, because the way when you use Jupyter for the first time, it launches up a notebook in your browser. And of course,
honestly, the hardest way to use Jupyter is to try to use it locally, because you got to install it and configure it and run it and get the cloud story is just even easier.
Exactly. So, we now have the scientific community who, like scientists, huge number of scientists in many different languages are all just used to the idea that we're going to do our science in our browser through this type of, IDE essentially. And Jupyter Lab especially has so many more features than classic notebook that make for a really rich, interactive scientific computing environment. So then moving the work to the cloud is trivial. I mean, for the user, and so in Pangeo, we operate some cloud-based Jupyter hubs. And also we have been operating a binder. And those Jupyter hubs, basically you just log on, and anyone out there can actually sign up for the Pangeo hubs or apply to get access to these hubs. And then you just have a notebook environment in the cloud. Of course, just having your notebook in the cloud is not that cool, but what we can augment it with are some capabilities to run Dask. So we use Dask Gateway in those hubs as a Dask deployment solution, but Coiled is another example of a Dask deployment solution. And then the key, though, what is going to bring scientists to the cloud is that data, right? So that is what makes this, appealing and game-changing. The fact that now you log into this hub, okay, you're in Google Cloud US Central 1. We got a petabyte of data from the World Climate Research Program, Coupled Model Intercomparison Program project sitting there. Organized, analysis ready, that you can start doing science with. So before that, if a grad student, say, would decide, okay, I'm going to work with these climate models and do this research project, they would literally spend months downloading, organizing, and sorting that data on a computer before they can get started. Now you can get started in 5 minutes and be processing data, and that's
amazing.
That's what gets me excited and motivates me to devote energy to this project.
Yeah, maybe that also involved writing a grant so that you could get enough compute to locally hold and work on that. And you got to wait. Okay, I'm going to order our Silicon Graphics or our Cray or whatever it is you're getting, whatever the supercomputers are these days, and they'll wait for some big thing to show up. Or you fire up a notebook in AWS. Take your pick, right? I suspect this is also democratized computing somewhat as well, right? You don't need as much compute to set up something like this and access that existing cloud database.
Yeah, I think that's true, and I think part of that is we've separated in the cloud model of separation of concerns. The storage is not necessarily directly attached to the compute, whereas like in a supercomputing center, it's all one warehouse, right?
Yeah.
And so like if you're doing a small problem, you get a small VM or you get a small cluster, a small Dask cluster. If you're doing a big problem, you scale out,
right?
And so you can you can arrange your compute infrastructure appropriate to the problem you're working on. And the other thing is the way we're storing the data allows for partial queries of these large array. So the data that Ryan was talking about, the CMIP6 data, it's a petabyte in scale, but you don't have to open the whole thing and you don't have to load the whole thing. We're able to slice into that and grab out just the parts that are interesting for the research project.
Right, exactly. That's awesome. One thing I did want to ask you too about real quick before we're getting short on time here, but do projects like Jupyter Lite, which is Jupyter but running on WebAssembly in the browser, or the Python stack a little bit running on the browser, or PyIodide, do these projects offer any benefits to you all, or are you tracking them? Are you interested?
Yeah,
totally. I think it's super cool. Jupyter Lite and PyIodide. I think it really lowers the bar to providing just like getting something up and running. I would say that like the motivations for getting into Pangeo, for starting Pangeo, a big part of it was big data. Right, we have large data sets, right, and so we want to do data proximate computing. So by putting a hub in the cloud, we're putting our compute next to the data. PyIodide actually takes it back to the laptop.
Yeah. This doesn't solve the data problem. This kind of wrecks that, but it does give sort of computational capabilities without.
And if you couple that with something like Coiled or any Dask solution, where you can actually then call out to a data processing layer that is in the cloud, it would make the need for us to operate those Jupyter hubs potentially go away or reduce or go away.
Oh, that's interesting. So you've got the Dask cluster or whatever next to the data in the cloud, and this is just the handling the results of all that. Okay, I hadn't thought about combining those in that way. Very cool.
Well, if you want to process like many terabytes of data, you're not going to do it in your browser. You're not going to do it in your laptop at all. You do need a big computer, right?
Yeah, but still, like it certainly expands what's possible larger than like maybe the first impressions. Yeah. All right, guys.
Go
ahead, Joe.
I was just going to say a quick shout out. We recently added a Jupyter Lite example tutorial to the X-Ray homepage at xray.dev. So if folks want to go try out X-Ray really quick without having to start up a Jupyter Lab server or something, it's there and you can.
That's fantastic. Yeah, we've got Binder, which sort of creates a cloud instance to run all these examples, but a lot of them could actually just run like this, which is great. Makes it a lot simpler. Yeah. All right. We could talk for much longer, but I also know that we don't have too much time left. So let me ask you both real quickly the final two questions. Joe, you can go first. Going to write some code. What Python code? What editor do you use?
VS Code.
VS Code. All right.
Or Vim if I can't.
Okay.
I use Atom, and I feel like I'm behind the times, but like that's what I use.
That's like OG VS Code.
It gets what I need to do done, but I feel like I'm missing out on things. So I probably need to upgrade. But I do feel like my development environment is increasingly owned by Microsoft, and so I have some mild reluctance to switch to VS Code.
Sure, I hear you. Awesome. And then notable PyPI package, some library you've come across lately that you thought was awesome. I mean, obviously, shout out to Pangeo and all of its libraries.
But it's not a package. Like you can't.
No, I know.
Pangeo.
Yeah. I'm gonna go with one of my favorites, which is not something I came across recently, but I think everybody should know about it.
As well, sure.
Is FS-Spec, and it's a library for accessing data across a bunch of different file storage systems, and it is a game changer for working with remote data. Everyone should know about it.
Yeah, absolutely. That's a super interesting one. Basically, you can connect it to all these different backends and stuff, right? I don't remember where to find them, but yeah, like you could connect S3 like it was a file and stuff like that, right?
Yep, exactly.
Yeah, fantastic. All right, Ryan, quick.
Well, mine is a shameless self-promotion, but it's for a new project we have called Pangeo Forge.
Okay.
Which is basically an ETL tool for this X-ray scientific data space, right? So what we found is that a lot of the ETL tools that exist for business style data analytics don't necessarily play well with our multidimensional data model that we use in
Okay.
geosciences and sciences more broadly. And so we're building this open source Python package called PangeoForge Recipes that is designed to help us with all this data movement, data transformation that needs to happen as we're migrating so many sort of legacy data sets into this cloud native
Oh yeah.
format.
That looks fantastic. All right. Yeah. Good shout out. And we'll put a link to that so people can check it out. All right. Joe, Ryan, this has been a lot of fun. A quick final call to action. People want to get started with Pangeo. What do you say?
Come to our forum, right?
Yeah, you mentioned before we hit record, you mentioned that the discuss page is like really where the action is at right now. The discuss forum, right?
The
Discourse, sorry, not discuss.
So,
Discuss.
so I mean, the tools are and the stuff is self-documenting on the website, but what we really emphasize about Pangeo is the community aspect of it. We are not just trying to build a tool and like put it out there. We're really trying to build a community where scientists are talking to software developers, are talking to infrastructure maintainers, are talking to data providers, and are collectively sort of trying to keep this flywheel spinning of innovation and development, ultimately with the goal of empowering more scientific discoveries. And so, if you have questions, if stuff breaks, if you don't know if it's the right tool for you, this forum is where we can welcome you. We don't have a Slack. We try to be more open as a community than a Slack. So this is where the discussion happens.
I can second that. It's a good idea. Awesome. And then Joe, you also wanted to throw out xray.dev, right?
Yeah. So exactly. This is a relatively new site that sits on top of our documentation site, but there's the JupyterLite interface is down below the fold, and it's a great starting point for folks.
All right. Fantastic. All right. Thank you both for being here. This has been really interesting, and thanks for all the hard work.
Thanks for having us.
Inviting us.
Yeah, you bet. Bye.